Yeah. Okay, hello everybody. It's time for us to start today. So really happy to introduce Davor. Davor is from Granlund, and I guess he will tell a bit more what Granlund is doing and so on. But you will learn again, I hope, something new about how to do these things in practice and how to do things with time series in particular.
Yeah.
So Davor, please.
Hi. So does this work, by the way? Yeah, good. So hi, as Jukka said, my name is Davor Stjelja. I am AI lead at Granlund and also a PhD student at Aalto. And I'll talk about drift and model retraining in time series prediction, mostly time series prediction. And I'll show one use case from relating to building energy consumption. So basically I'll tell you what are drifts, what are some potential drift detection methods, retraining strategies once you detect the drift, and then also advanced kind of continual learning methods. Then I'll show example what we did for energy AI, our own kind of energy product, not product yet, but soon to be. And then talk about human in the loop in this, and then as a bonus, of course, I'll talk about large language models and drifts, but that's a few slides only. So first, shortly about me. I'm coming from Croatia, and I've been in Finland since 2015. My major is mechanical engineering, but then since I started PhD in Aalto, I learned this kind of data science, machine learning in that world, and then from beginning of this year, I became AI lead at Granlund, and so on. Granlund, so it's a Finnish company established in 1960. It has now, I think, almost 1,500 people, and it's 100% employee-owned. And it operates in building sector, so mostly design, operation, consultancy, and everything related to built environment. And we invest a lot in the innovations. We have a lot of research projects, like one with University of Helsinki about scaling machine learning ops in industrial environments, and so on. And as you see, these are kind of some areas in a building that we work on. So coming from, we don't like do we don't do much architecture in that part. That's very few we have on that, but it's mostly about the systems in buildings. So we have like a lot of data from different sensors, especially as the buildings are becoming more and more smart. You have like a lot of devices, actuators, sensors that you can control, and that's some interesting data that we have. Other type of data is also, since we are a design company in consultancy, it's basically reports, drawings, building information models, and those, and there's also a lot of data that we try to utilize with AI. So what are drifts? So drifts, basically machine learning models in this particular case are designed to reflect real-world scenarios. So even if you have a great model, after some drift occurs, that model, since it's trained on the history, it becomes inaccurate. And then, of course, you cannot trust it anymore. And you need to do something with it, either retrain it or have a new model or something. And this is example from one building's electricity consumption. I think it's a university building at the start of COVID, so at March 2020. At the beginning you don't see, maybe I should have put a bit earlier data. It was, our prediction model was pretty close to the reality. Reality is gray in this image. And then, but immediately as lockdown started mid-March, they kind of start to lag, like, or there's a big drift, the difference between what we expect to be and what happens. And kind of buildings are like that, they're very unique. And and also they are changing all the time. So it's very difficult to have some generalizable model that will work in every scenario. So what kind of drifts there are? There's two main types. So there's a concept drift, which basically is a relationship between your input and output, and and if that changes, then the model is wrong. Then there's also data drift. That means that just your input data distribution changed for some reason. You have never seen that kind of dynamics in the data or something when you were training it, and and then you see the drift. This is from, I think, DAL-E image, how they said drift of time series. I don't know, is that good, but yeah. Then what types of drifts there are over time? So especially in time series, you have like these blips. That's basically one time only, or sometimes it happens. You have this recurrence, so they start to happen in some frequent manner. Then you have incremental, which slowly change from some normal behavior to abnormal. And then also gradual in a similar manner, and abrupt is like completely stops. For example, maybe that COVID start in that building could be abrupt. But then when we come to our use case, we don't, for example, consider these blips. This is something what's not important for us. It's only this kind of that are continuous and repeat frequently. So then I'll say about some drift detection methods, some basic ones. You can read more when you have time. But these are some standard drift detection methods. So you have this kind of, I'll say next slide what does it mean, DDM and ADWIN, but it's drift detection method and I think adaptable window method. And they basically differ in the way they work, but the idea is to kind of monitor either error rate or something else, and then you either decide yourself as a human what you will do, or you make a system that will automatically do some action of retraining or whatever. Basically, mainly two are the most popular, this DDM and ADWIN, and then there's also custom methods. Actually, we use the custom method. I'll mention how that works in a while, but that can be like more specifically for certain application, and it requires some domain knowledge. So drift detection method is DDM. It's kind of the most basic one. It basically monitors the error over time, and it looks at the typical error and then like standard deviation. So if you have two standard or higher than two standard deviation, you have like a warning, and it kind of stores those things. And then if it's more than 3 standard deviation, then it's definitely change. So it kind of stores those errors, and when they accumulate, they are visible, and then after that has been detected, they are kind of reset. It's kind of generalizable approach, and it's simple to use, but there are some potential limitations. So it might be too slow in responding to changes, and accounts for both magnitude and duration of changes. So let's say if you have a high magnitude, it will be detected immediately, which also might be that it can give you false alarm, I would say, because if that's not repeatable, I'm not sure, is it then considered as a drift maybe. But if it's lower magnitude issues, then they also might take longer to detect because it accumulates them over time.
Davor, can
Yeah?
you say what is P and what is S?
S is standard deviation. I think P in this context is error.
And how do you get P and S from the...
So it takes, I think, from the From the training data set, I haven't applied this method. I was just studying it, but it takes from the kind of a typical error that you would expect. So you take some test data set, or you could even maybe do with training data set, depends. But then you just check what is the typical error, average error, and then a standard deviation of those. And then you put a threshold of 2 or 3 standard deviations for like a significant error, and that's how it.
Is the standard deviation? It's like you have some assumptions. Is a probabilistic model or like?
Doesn't need to be probabilistic model. Just a regression model, any kind of like. But you kind of monitor. You know the ground truth, and you know your prediction, and then you monitor this error between, because it's never zero, of course, and then you just look at how is their distribution and so on. That's in simple explanation how it works. Then if we go to the next one, is this adaptive sliding window. So that one kind of has dynamically sized windows. So it has different sizes, and it kind of always has the most recent data points in them. And kind of it checks the average value within the window. And if that average value changes a lot, then it suggests the potential change or a drift in that window, in that data stream. So kind of it's more unlike the first one. You need to kind of define that, okay, it's 2 standard deviation, 3 standard deviation, but this one is more dynamic, and it will kind of also know when did the drift happen, because it kind of looks at these windows. So it kind of has a smaller window, they're larger, then it kind of increases it, I think, until the start of the data. And then you kind of know, okay, since in this window this error was present, but if you go further back, then it doesn't show that error. But that can be more computationally demanding. Yeah. I have like studied these 2 methods, didn't try much because actually tried it a bit, but the thing when we were developing our tool, we wanted more informative drifts. So these are kind of very like based on some statistics, but we actually knew what kind of drifts we want to detect. So then we made a custom version, which is actually very simple, but I'll show in one of the slides a bit later. And as I said, these are 2 main, these DDM and ADWIN. I have seen it in many different papers. There's other version like that, if I go back. KSWIN, which is, I think, using Kolmogorov, Smirnov, test for that. Then it has some others, maybe you should check those. But there's like million variations of that. These are kind of simple ones which detect drifts. But once you detect drift, you need to do something with that. So like you need to do retraining, or it can be a new model or whatever is for your use case. But here if you focus on retraining strategy. So one thing is, as said, those just detect drifts. They can be made that they are kind of part of the retraining strategy. So if it detects that in this window, from this window the drift has occurred, and now you have a new data distribution after that time, then you can make that, okay, from that time you take the data for new model, or you kind of combine old and new and so on. So these are some retraining strategies. First, I'll tell you a bit simpler ones, which are applicable to, I would say, any machine learning, supervised machine learning model. And then a bit more advanced ones, which work more for deep learning. Basic is static model, and this is just basically trained once on historical data set and never updated. It's most common in research, like you use a sum toy data set and you show the best accuracy ever, and that's it. And that I had the biggest problem in my PhD. I had these million papers about either predicting energy consumption in buildings or detecting occupancy in a room based on the CO2 measurements and temperature measurements and so on. They all had this kind of like very static, as it's mostly research, and then I'm trying to apply them in real life, and it's kind of okay. I had a great model that showed really good accuracy in energy prediction, but then on some data it shows really bad, on some good, on some bad, and I'm like, why is that so? And then I went to check the training data set, and then I kind of saw that there's drifts in my training data set. So I was like, how the heck I'm gonna like scan all of the, if I have hundreds of buildings, do I manually go through all training, which can be a few years even, and check if there's no any drift and what to do if there is. So then I needed to find some more automatic, and then I started to look into these methods. So one basic, yeah.
When you say there's drifts in your training data,
Yeah.
it doesn't really make sense to me. Like your training data is your underlying, data distribution.
Yeah.
For me, you can define some convex hole over your data set, and then whenever you're getting new data, the problem is that it's not fitting in this convex hole, or it's just a different distribution. Like you showed these different, the circle in the star.
Yeah.
So what do you mean by?
So basically, there was not there's no model drift, but there's like in this case building drift. Building has drifted. So if I have a half of data set which building had this behavior, and the second half of training data set it had different behavior, then the sum of all that, like it's crap. Like it's not useful for the first case or the second, because it might be okay, but it might not be. So it's like, let's say if you have in our case, if you take COVID, you had office building which was populated from 8 to 4 Monday to Friday. Then COVID came, it was mostly empty. And then if you take this data and try to predict this will be wrong. But if later when I trained on the COVID data, then if I go further, okay, now it's kind of something in between. People are not going that often to office, but are coming more. Again, it's not a good representation. And if I take all of that before, the pre-COVID, during COVID, lockdown, it's again not good for either of those. So kind of I had that issue, and then if I go manually label things and which are good for my training, then I spend too much time, and then I lose what I wanted to do here.
I guess I thought of this as like kind of a model selection problem.
Yeah.
If you have two different kind of sections of data, of course you don't want the model to just get the mean.
Yeah.
Because the mean is pointless.
Yeah, yeah.
So I thought it would be more like a model selection, but you're saying that instead you want to train maybe specifically for like pre-COVID and
Yeah.
have a model for COVID and then have a model for post-COVID. Is what you're suggesting.
Yeah, I think of course depends on a use case. I'm talking from my use case perspective, because as I said, buildings are unique. Like every building is built differently, and even if you find two exact same buildings, they might occupancy might be different. One is like a university building, populated. It can be even in the night people studying, and next is like, I don't know, government office working from 7 till 3 on Fridays, maybe 2. And then rest is empty. Like, and they're completely same buildings. They will have like completely different energy consumption patterns. So if you want to kind of capture the dynamics between weather and date and time, and then the consumption of that building, you need to have kind of updated like that dynamics, which is kind of abstract to otherwise do. But maybe for some models which are more where the problems are not so dynamic and they're not so unique, maybe you can do this kind of some other thing, because saying that maybe pre-COVID information from that building in some other use case could be useful, while in my use case I'm not sure even if it returns then the model to that, but yeah. Like for example in large language models, I'm not sure how this is maybe a different concept there, for example, because they study language, maybe it doesn't change that much language and so on. Then if you go to like the most simple kind of retraining strategy is expanding model. So basically you have like some first initial training data set, and then you get the new data on which you infer the model, and then you go to the next time wherever is the retraining. Is it something like you do daily, monthly, yearly, or is it because of some drift detection, and then you start the training? But the thing is that next time you do the retraining, you take that newest data and all of the history, and you train basically a new model. So in every case you have a new model starting from scratch till the latest data. That's one thing which can be good in some cases, but then in referring back to my use case, if the training data set is small, relatively small, then if you have, let's say, I don't know, a new data that's 1/3 of it, 1/4, 1/5 of that, then it is going to be kind of fine to also learn these new things. But as it becomes bigger and bigger, the fraction of the new data among all of the data becomes so small that it might be not visible if you do any retraining this new information. So that's why it's maybe not the best scenario, but depends on a use case. Then the second is kind of rolling model. So you have a fixed amount of training data, let's say a year, and then you have 1 month of new data, and then you once that month passed, you take last year from that moment, and then you take the next month and so on. So that one is partly the one that we used, but that one kind of gives more flexibility. But again, for our use case on its own, it was not the best, because again, you have maybe drift happens in last month, and you have a year of training. So again, if it will take probably 10 times that certain new pattern reappears, or even more, that it will be catched by this model. So using on that own the model like that, it will give us the errors that we wanted, or detect the drifts that we wanted, but it won't learn them that quickly. It will take a long time. It will give you basically a lot of false alarms after okay, I know that there's a problem, or there's no maybe a problem, there's just how the new pattern is, but I don't need to be reminded again and again and again. So that was the thing we didn't like in this model. So we needed to go to the next step. And then we just said, let's use an ensemble. So ensemble, basically it can be ensemble of anything. It can be ensemble of 2 different methods, 2 completely different algorithms. Not only 2, it can be tens of them. It can be of many different retraining strategies. But in our case, we are using an ensemble of 2 rolling window models. So one we have a long model, and one we have a short model. I'll tell you in a while how does that work for us. Now I'll tell more about advanced continual learning methods. These I haven't tested, so I just from one very interesting paper from my field. Yeah.
In your experience, like coming from a company, how dependent is the retraining strategy on your compute budget? Like, because okay, it's an academic, we normally don't care about the budget, but maybe you have some.
So I'll tell you more about the model soon, but it's basically based on XGBoost, basic of the model, and that one is really efficient. Yeah.
Okay.
So in that case, it doesn't. Like, since this is not yet a product, I think next month, now the software guys are working on it. Hopefully next month will be maybe a release or something. Then I think it's not going to be a problem in the first iteration, but maybe when we have hundreds or thousands of buildings, maybe then we need to do optimization. But that's kind of the thing is that we don't have any use case that that we will have immediately, like I don't know, million subscribers or something like that. So we are just doing iteration. We will see it works good enough now. And then we'll go after. Main point was to make this thing possible, and then and good enough for start. And then in the next stage we can do, like, I'm thinking now we are doing retraining of the longer model once a month and the short one every day, and that's pretty fast. But the problem mainly is that, as I said, buildings are unique, so you cannot have one model. You have if you have 100 buildings, you have 400 models, because you have we are monitoring electricity consumption and district heating consumption, and each of them have different aspects, so they need different models. And if there's an ensemble, so it's ×2. So that's something what we have actually in the IML4E project with Jukka been working on, this kind of monitoring big amount of models, but they are luckily computationally easy. But I have some ideas to make a more generalizable based on deep learning, which will again be actually much bigger, but there will be less amount of them. But we'll see.
Yeah, because it will, like, you have to retrain every day.
Yeah.
Some people just can't afford this.
Yeah, but depending, these are very small scale model. Like on my laptop, okay, I have a good laptop, but still it takes, I don't know, for a short model. If the daily is like second, so you have 100 models on some cloud somewhere, like, and it's not done in real time. It kind of we get the data with a lag. We get once a day for the yesterday. We get the consumption of the building, so it's kind of during the night at some point. So far it's not a problem, but we'll see. It's a good question, yeah. I have talked. We had actually last week also with Jukka meeting where there was F-Secure, and they were asking me something in that manner, but because they have their security company, they have people are using it like in big numbers, and they need to, like, when you open a page or something, they need to check some things. So it's like very quickly things need to be done for a big amount of people. But in our case, it's like once a day for maybe few hundred or few thousands max in the near future. So it's kind of like less of a problem. And these are not big models. So actually they're bigger in size. If you use all these kind of tree-based methods, they are actually a model itself. It can be like half a gigabyte, but it's very quickly to train. While if you have a deep learning model that you maybe train for like hours, can be like few megabytes. So it's kind of, in that sense, it's bigger, but yeah. So these are, now I'll tell you of 3 advanced, more like continual learning methods, because these are kind of the one I showed previously are not actually continual learning. They're more kind of like trying to do static models in a continual manner. And these apply to deep learning, mostly. I haven't tried them, so but they are really interesting. And in my future work, where I try to learn more deep learning or use deep learning in this case I will try to use them. So this is from a paper about building energy prediction, and these are kind of 3 methods. They're more kind of all of them. Also, this goes to the previous methods as well, that it's kind of a balance between stability and plasticity. So kind of not forgetting important from the old knowledge, but adapting to the new information. And there you have 3 methods that are kind of 3 basic methods are these kind of regularization based continual methods. So you kind of take some from parameter importance from the old model and then you update the new one. Then it can be this memory replay, so you kind of take some representative samples from old data to the, and then you train a new model. And then it can be this neural resource allocation where you just expand the network, so you just add more nodes that has that is trained for the new data, and then there's different variations, but they kind of try to like minimize that it doesn't grow too big, because after a while it would be useless. So one is this regularization base, so kind of it adds constraints to the loss function and ensures the preservation of important knowledge from the previous task, or it can be from the previous data. It can be the same task. And it kind of dynamically assess and maintain the significance of certain parameters, and kind of the said key is balancing this new and old knowledge. And I think there is some parameter lambda in those methods where you kind of define, or depending on a method can define how much you take history and how much is the new data important. So we have here 2 listed main methods. One is elastic weight consolidation. This was developed by DeepMind, and it kind of adds to the loss function quadratic penalty based on the differences between current and previous task parameters, and then it kind of assesses this parameter importance, and using that it balances this hyperparameter lambda, which kind of balances old and new. Then you have this synaptic intelligence. It's basically assessing the importance of individual synapses, and this one can be done in online manner, unlike the other is in offline. So it's kind of more real time. You can. This is more for you if you want to read more of them, just as an intro. Then there's this memory replay based continual. So kind of you take some sample of the old data, and that depends again on certain parameter, and you try to find optimal mix of the old and new to kind of when you're training the model. And one version of that is that gradient episodic memory. So it stores the past data or constraints of it, and when you are learning new task, it kind of checks for the old ones that they don't go out of the boundary, and therefore ruin the prediction of old things. So it kind of has this episodic memory that use calculate these gradients, and then kind of use that to check the old, and then you learn the new, and so on. And the last one is this natural resource allocation. So as I said, this is basically just in brief, it's enlarging the network. So you freeze the model that has been trained on the previous task, and then you just make it bigger, and this bigger part learns these new things. But then there's different approaches how to make sure that it doesn't like grow too big. So there's this kind of pruning method, like this packnet strategy. So kind of to see which are unused in the old tasks and so on. But I think with all, like without trying these methods, it's kind of still important what is the reason behind the drift, because these all methods kind of go into, okay, we don't want to forget what happened previously. We want to learn, but we want to learn the new things. But it might be in some use case that maybe that previous thing is not anymore relevant. So if you just have completely automatic system which will detect drift and use any of the methods, simple or advanced, again you will just combine something that's not relevant with relevant information. So you shouldn't maybe rely too much on that this works automatically. And probably these advanced methods, I could see that because they're kind of like still keeping parts of the old, and that continues and continues and continues. You should do some kind of regular checks, like, okay, if there's some while, does this make any sense? Should we just like have a new model for this? Because in my experience, when I tried some methods, not those that are kind of more continual, I was using like probabilistic machine learning or versions from gradient boosting methods that are probabilistic. Even if I managed to get like the regression part fine, but then the predicted distribution was like something that doesn't have any sense anymore. So maybe after a while you should do some check and say, okay, now we have, especially if we are looking at time series, that's continuous kind of, you're getting new and new data over time. These are good, I would say, in the first stages where you have like fraction of the new data and a lot data of old. But after a while you will have like a big amount of the new data. Maybe you don't need any more this old. You could just like, okay, restart from that and go on. So just some things that come to my mind related to that. Then I'll tell you about our use case. I have already said many things, but so basically, as said, buildings are unique, and basically in the simple manner that means you need to train each model separately for that building. You can train, I have actually tried to train like a big model where I have, let's say, 10 buildings, not even that big, but and use the one model to predict those things, and they work, it works very fine. If it has enough descriptive features, then it can describe that, okay, this building is like that and that building is like that. But then again, you have a drift, and drift are not synchronous. So if it happens in one building out of 10 and I retrain the model, it might happen that it screws up the prediction of 9 other buildings which didn't have any drift. So especially for this retraining purpose, I decided to use like individual model for each building, because they're all independent from each other. There's no any relation except they are located in Finland. Other than that, there's no anything common. So why would I use one model for that, especially when they are kind of in a continuous manner? So that's one thing also that you need to check. Is there a point to have a generalizable model, even if it works in your kind of static scenario? I managed, as I said, I managed to make a static version that works very well for all building, like one big model. But then, again, a drift happens, and then it might be that you change something you don't want to change. Maybe you don't, but then again, yeah, it's difficult to check that. But yeah, anyway, we are we are trying to do two things. First is detect changes in buildings, and by changes we want to know repetitive changes. Since buildings are not nuclear power plants, we don't care if there's like 1 hour, your energy consumption was weird or too high or too low or something. Nothing is going to happen. And anyway, we are predicting here history, so we are checking for last weeks. Was there any problem? Even if there was like yesterday 1 hour weird, and we cannot do anything about it anymore. So what we want to know is if they repeat, if they're like in the nighttime, the energy base load should be like this, but all of a sudden it's not, and that is repeating, then it becomes a problem, and then it's systematic, and then we can do something. So that's why we wanted to create our own kind of way to detect these drifts, because we know that we are interested. Like we tried a version of this first DDM, where we used basically a standard deviations, and that's the thing is that we got a lot of alarm that are maybe not alarm, and we got too many of them. What we wanted to get is to get, let's say, if they're repeating in similar time of the day, in similar day of the week, and so on. So that's why we created the method. I'll still mention that. And the other thing, not only this kind of creating alarms from the energy consumption, we wanted to detect day ahead forecast. So it's basically using the same model, just takes the from the forecast, it takes next 24 hours of the weather data, and then it says how much your building should consume tomorrow. That was very interesting a year ago when the electricity prices were super high. We had from some big customer, like, we need it now, and this was still like, we didn't have any MLOps yet capabilities a year ago, and it was kind of, okay, we are very hurried to do this, but then in few months after winter, the prices went so down as they are now, that they don't care anymore. So I don't know, will that be any more interesting for a while, this day ahead forecasts, because like they're like, that's what our consumption is, we cannot do anything. But then one very potential problem that might happen if one day we start to use this, what's it called in our field, demand response, which means that you would change your demand based on the availability of energy. So now, especially with the renewables, if you have too much wind, they might have big problems, and you need to store the energy somewhere, and you can turn off certain. That's already done for decades in like big industry. They turn off certain electric motors of the grid. But we can do that in buildings, but buildings have very small potential, but there's many buildings, so you could do that over time. There's also opposite problem when you have too much energy, that you actually ramp up. So in case of ventilation, we would maybe turn on the ventilation for those few hours when there's too much energy. You would actually get money to spend. But the case with that, if that kind of becomes ever a thing, they have been talking of 10-15 years that's coming. Last winter I thought it's coming because electricity was super high, but then again nothing. But the thing, if that happens, is that if you predict future, that means someone knows the future. That means that someone will react to the future, and they will do the change. And then what do we do with our model? How will that affect our model? How will it mess up? Because if they do the change, and if we do just typical retraining what we do, it will learn this change what they did. And next time that happens, it will say that, because it will think that you will do that change. And it will say, okay, your energy consumption will be very low tomorrow, even though the prices are super high. But actually, I don't need to do anything. It will be good. and then they go. It goes very differently than what you predicted. So that's, I think, the future problem if this demand response happens. How to do that? You need to have a better process. Like now, this is more automatic. Buildings just go on their own, and our model learns on their own. But there should need to be like some feedback loop. We did something, and that a bit complicates the process. But yeah, that's one interesting thing. And this kind of works with electrical consumption, district heating consumption, and solar panel production. Only issue might be with electricity consumption of residential buildings, which we don't we don't work with those that much, so it's okay for us. But using how people use electricity in their homes, it's pretty random, so it's not maybe as in this building or some other commercial buildings. Heating is, on the other hand, more temperature based, so it's not a problem. Then how does this work? So we use this XGBoost LSS, so it's kind of a version of XGBoost which has location, scale and shape, so it basically predicts distribution. It can predict almost any distribution, but you get not only a point prediction, but you get the distribution of it. And that's important to know the threshold, because it's very dynamic. So if we have, let's say for heating, if you have warmer part of the year or colder part of the year, if you would have a fixed threshold, let's say in summer, we would have problems. Believe it or not, in Finland, heating works in summer. So you also, but it's very low. So what we use for winter, it would be like, to be very difficult. So that's why fixed threshold doesn't work. So we needed something to predict our distribution based on the inputs. And I was testing even some more probabilistic Bayesian methods like this Gaussian methods and so on. But the problem is that they're slow and the results were not good. So then kind of this is a frequentist approach to the basically to the probabilistic method. It's a very new package, this XGBoost LSS, but I recommend it. It's pretty well maintained, and they have just released new version which uses PyTorch in the back, and then you can test many different distributions and use them. But basically there, after that has been done, we need a retraining strategy, and we need to first detect drifts, but also a retraining strategy. And as I said, we used ensemble rolling window. There's two windows. One we use 1 year and one month. And this one that is a small model of 30 days, that one is retrained like daily because it's super small and it learns quickly, while this longer one, we do that it's retrained once a month. So basically in this case, we are actually not using drift detection method. Like our alarm matrix is kind of detecting drifts, but we don't use it to retrain our method. We could do that. Maybe we do at some point. Maybe if we go to optimization after a while to make things use less resources, maybe we do that. But now we kind of just by the time retrain. And we use this drift detection method for what we need. So basically, how does it work? It's very simple. We got, first of all, from the initial project version, which we just used 2, or even 3 standard deviations at some point of the errors. Then we kind of got many alarms that might not be significant, and then we also got alarms that that, or we didn't get alarms that we should have gotten. So then we kind of talk more with the consultants that actually are going to use this, who understand those buildings that we were working with, and they said that it's critical to detect recurring anomalies. So let's say what might happen, that something as simple as someone has left ventilation on, like they had mostly in most of the buildings ventilation is programmed by schedule. So you have a calendar, and then you have for Monday to Friday this time, especially in the offices, and then you have like it ends, I don't know, at Friday at 6. But they had some party in the office, and then someone made a manual override that it works like the whole Friday night. And that often, because those systems are not smart, it can stay like that. So every next Friday will be like all night will be working. And that's a pretty common, even though it sounds stupid, but it's pretty common. And these kind of things happen, or people start to come in different times to the office, and that also changes the pattern and so on. So we kind of want to detect repetitive things that we can work on, because, as I said, something that happened in history we cannot anymore affect, but from the history we can learn, and we see, okay, this is repeating like that. We should check if there is such a problem, so that in the future it doesn't happen anymore. And then we develop this alarm matrix, which basically checks when every day we get new data, we run these models, and then if there is a point that goes outside the uncertainty boundary that we got from our probabilistic method, then check, has the same thing happened in similar hours of the day, so couple hours before, couple hours after, in the previous days, and also check, did it happen in the previous week, like the same weekday, because those errors can often be like, as I said, same Friday or same, so you check couple Fridays back. And then if you see that they have been outside the predicted threshold, then make an alarm and send a notification to someone that there's a problem. So as I said, buildings are constantly changing. This is some building somewhere. Here it was pretty fine, mostly inside the predicted lines. There was some problem here, but okay, that didn't happen that much. But then next, I think this is weekend, next weekend it goes outside boundary, and then next one again. And actually base load, if you look the whole night time, night is when there's this valley, you see that it after May 25 it goes outside the boundary, and that is let's say what we want to first detect. But then if this continues to happen, we don't want to get alarm, and that forever. We want to, okay, if this continues to happen, then we assume that it's a new normal. So we want the model to learn that and not anymore show us how it used to be. So then, as I said, we use this long and short model. So basically, this is the same building, same time. Just this is the result of the long model, and this is the result from the short model. So, as said, this one is trained on a year, and this one is on 1 month, and this one is retrained every day. So it learns relatively quickly, and the things that are very similar, it learns quickly. But if you look at the long model, you see this is, I think that was a Monday. It starts to happen, something starts to happen on those Mondays. Or was it Sunday? Anyway, the gray line goes above the line. There's a new, some like much bigger energy consumption, and not only 1 hour, but a whole period of a day. And then repeats again next week and again and again.
Stick somewhere if you want one. So there's an old-fashioned stick.
Stick. Yeah, I see. Yeah, this one. So basically, yeah, it happens here, here, and then again, and again, and again, and again. And then these green things are basically are weekly repeating patterns. So this is that it has, we programmed so far, speaking with the experts, that let's say if it happens 2-3 times that they would like to know. So we managed, if it happens once, nothing, and then third time it happened, then it creates an alarm. So in this case it will take 3 weeks to detect this problem. We can make that it shows here, and then if someone really wants to check, they can do, but we don't want to spam people. So is that because the problem is that now is that thing is not detected at all. So even after detecting after 3 weeks is better than after detecting, I don't know, after a year. But the problem with this model is that it continues to show these errors. So okay, after we have now noticed this, I guess some expert has went and checked and maybe said, okay, I don't know, we have something happening in that building that day, it has higher consumption, like there's no problem. So okay, we want to learn this new behavior. So then we have a short model, and that one, if you see, it also shows here error. It showed also on the same week error, but then it already after that it doesn't anymore show error. But why don't we use only the short model then? It's much more efficient and much smaller, because it doesn't have a seasonality, because it has trained only on last 30 days. So here, this is February, there was one very cold day, and it has never seen that cold before. Of course, it will give some errors here. We don't want those errors. So that's why we kind of use the combination of those two. And then we kind of especially rank if it's like, if both models give some error, it's different than if only one gives an error, and so on.
So the short model was trained once a day?
Yeah, but on last 30 days, like a sliding window, yeah. Yeah, as I said, it misses the misses the cold days. And then we kind of combine these two models into one, and this is what we kind of in the end show to the user. How we combine them, there's many methods how you combine ensemble models. You can pick one, you can have an average or something in between. In this case we pick, because we know the good thing here is we know the ground truth. We know we have what is reality, so we are predicting what we already know. So then we just pick the model for that day which had the best accuracy, and then we kind of show it over time. So here, for example, everything is normal, then the COVID started, that's the graph from the beginning. But then we get these alarms. First we get this yellow is daily, so if after 2 days it happened, then it shows, and the green one is weekly, so after 2 same weekdays it shows, and then it learns over time the new pattern, and it's kind of automatic, even though we have ML ops, but it can work without any ML ops. In this first version is completely automatic. Maybe it's not the best for some things. Then, as I said, it would be good to have human in the loop. So this is something important to mention, because you can have all these advanced methods, but you should have a human somewhere there. What we are now working on, also with IML4E, are kind of model monitoring, where also the idea is to monitor this over time, and not only, this is kind of fail-safe scenario that we have now that works in majority cases fine without any intervention from anyone, but we want to have also humans. So now we are building these dashboards with showing different kind of metrics, starting from data, checking data distribution that comes. Often the data for some building doesn't come at all, or there's some other problem, like in problem that we pick the nearest weather station next to that building from the nearby Finnish Meteorological Institute, and it has happened in Turku for some station. They just all of a sudden completely one weather station went offline, like they stopped maintaining it. So, and we noticed that after a long time, so we should have something to check these things. Then we also monitor like infrastructure things, like how much is our cost in the end and so on. But also the thing is that we need to have something that people can give feedback as well, our users or our consultants. So for example, in this case, they would say, okay, this is something that's important to learn, but these are some like glitches in energy meters, not actually any building change. So maybe you should not learn this, maybe you should forget this, and so on. So that's also very important thing, and this can be maybe you can have like a automatic. That's what we plan to have, like automatic, that it works on itself. But then every now and then someone checks this, and then maybe repairs potential problems, because it can happen that building goes under the maintenance, and then it's like, I would say, offline for a long time, and then someone needs to say this building now has some renovation going on, doesn't work, and after that probably the pattern will be completely different, but we need to see, and so on. Yeah.
So how is this forget thing reflected in the next training material?
So that's a good question. We didn't do yet that. That's a good one. The simplest thing is just delete it from the training data set that day or that hour or whatever. That's maybe the most simple thing you can do, and probably won't have any effect. Why not to do that way? Maybe you could somehow clean it, maybe something like that. So you would train a new model, so you don't forget it, basically. You just make it sure that the next version of the model doesn't have that in the training data set, but you don't kind of actually forget it. Yeah.
Trying to predict the grey box, and then you don't use it as training data, so then predict after the grey box if you delete it.
No, I mean, if you look this as a history, as I said, we use 1 year of history for the training of the long model, and you do this happen, I don't know, a month ago. You just, for the next version of the model, you will just remove that day. Like it will just be 1 day out of 365 days less in the training data set. So in that case, but for your forecasting, we are not actually doing the forecasting that you kind of only based on history. We actually use the future for forecasting future. So we use the weather forecast. That way, but of course we use some of the features from the last, I don't know, 1 week and so on as forecast. But yeah, that is something that we need to check. But I think bigger problem than how to do that technically in the model is the process. How do we get feedback from someone who is going to use that? How do we get the labels? Who does that? How? What is the interface? How do they? Because how this is going to be deployed is in the end just a Power BI dashboard. Power BI is a nice pictures for directors, but it doesn't have like two-way signal. So you cannot send back. You can only view the data, but you cannot do something with the data and send it somewhere. there are some workarounds, but that all is clumsy and maybe not the best. So there's more problems like that than actually what to do with the data or the models themselves. Then my last thing is I'll talk about few slides about LLMs or drifts in large language models. I need to add this because we are not yet. This is more like a plan for the next year. We have a lot different kind of applications that we will use large language models, and I have just been starting to work on them. And since I was doing this presentation, it came to my mind maybe you should mention some potential drifts here, because that's completely different meaning of a drift there than what was in the use case I showed you previously. So drifts in large language models can be abstract. So maybe the simplest thing to explain would be if people start to use differently the language. So then it will be maybe wrong or different. That's probably not evident in the human languages, but in programming languages is pretty evident. Already now some weeks ago I tried to help myself with coding using ChatGPT, the GPT-4, and the code gave me an error. And what was the error? Basically because I have new pandas, so it's 2 point something, and this one doesn't have that. And they have done some changes. I think it was about about pickle files. The pandas now have like pd.read pickle or something. Before there was not, I think, integrated reading pickles inside pandas, and it doesn't know that, so it gave me like something that doesn't work anymore. There was some different syntax. So that's maybe one visible thing that it can happen. But there's other things that are more maybe model related that can change, like something inside the models which are very big and closed, so it's difficult to say what exactly changes there. But you can see that models have changed. I started to use GPT-4 maybe when it came, I don't know, in spring, and since now it's different. You can kind of see it, and there is metrics to show that it's different, not in a good way. Maybe performance-wise it's better, like it's much faster, but the results are not as good as before. But then also there can be prompt drift, which means that if you have the same prompt in a different time, it will show you a different result. That can be maybe because of their changes, or somehow how model, it has a bit creativity, a bit randomness, so you can get that. But that can be a problem if you start to make applications on that, and I'll show in a sec what do I mean by that. But this is from one paper. They have basically tried with different questions, either medical exams, math exams, or different kind of questions over time. So this is GPT-4 and GPT-3.5. This was done in blue is in March and the red in June. And this is kind of the accuracy. You see that GPT-4 was kind of, first of all, mostly better in March than it was in June. GPT 3.5 less. I don't know, are these absolute or relative? Does it mean that this is better than that, or just because this one had a smaller change? I'm not sure in that. Should read. There is a paper here if you want to read. But the thing is that what I want to say here is that they change over time. And they are tuning them or doing whatever. Often with GPT-4 it mostly went with sensitivity, so at the beginning you could ask some murderous questions, now you cannot anymore. Yesterday I wanted to do some health check, now it doesn't at all. First answer is just go to doctor. But then when I said this is only for the research, then it kind of gave me some answers. But yeah, they added more and more of that because of, I guess, the what they got from media or something to satisfy them. Maybe they kind of did more sensitive. But anyway, what happens is that they are so complicated that these authors said that it can be because they are trying to improve one thing that they make worse some other things in model. So in GPT-4 mostly they wanted to increase the performance because it was super slow and probably expensive for them. So then when they're optimizing that part, they might unwillingly change something else. As I mentioned in my use case with building energy consumption prediction, if I would have what I tried first, one model to predict tens of buildings energy consumption, then if one drifted and I retrained it on that, I might screw up some building prediction which was performing well before that. And then you should be checking all that and make sure. So it becomes more complicated. So why is this useful? So this is one idea that we have for one application for us. So in this case, this was just a small trial, but this is a small image from the schematics of air handling units in ventilation systems. This is basically a heating coil, and then there's valve, there's like hot water around, and in the pink thing there's air coming. So air goes through, the heats up and goes to the room. And there's sensors and valves to control that. So basically this is an image, and I wanted to create a knowledge graph of that so that I could make some in the end queries and make some checks, like if this valve is closed and this temperature is here, do that and whatever, or use some machine learning model for something. So I need to have it somehow that computer understands, and that's maybe to use some ontology and so on. So I gave it image and tell what I want to do, and it kind of did most of the things correctly. It said, okay, this is a temperature sensor, it has this measurement point, but then, for example, it's not perfect. For heating coil, it says it's battery-like symbol, so it doesn't know exactly that. But then it also found edges or relationships, so this thing is connected to that and so on. And then after that, it kind of created or tried to create some kind of representation in RDF format of this thing, and this is great, even though it had some problems, but it kind of understands the context. So it did many things. Like previously, you would need to have probably a deep learning model that from images detects these symbols. So you would need to have that, and that can be probably to be way better than this, more accurate. But it does only that thing, nothing else. Then you need to have maybe some graph model or something to kind of detect these edges. So like what is connected to what and so on. Also, it kind of understands the context. So it knows this symbol is a temperature sensor. And what is temperature behind that? And kind of it measures things in Celsius, not euros or kilos. Like it has this context which maybe some kind of image classification model doesn't have. And then also it created this kind of representation. So you would need to have some algorithm, some script that will from these models give you this output. So many things. It's very good in those things, but in none of the specific things it excels. So, but it's still very good. So my idea is to use it as kind of a orchestrator, so that kind of you take specialized models for specialized things, but then large language model is the one that runs things and says, okay, now you need this model to detect that, then call that model, do that, take the output, do something with the output, send it to another model. It's very good in that. But as said, the problem is that even if you make it work, they drift, and they also update them, and it's update them in a way that it's not transparent. So maybe in a month this doesn't work, and so on. So that are some problems that it might have. So I said there can be behavioral shifts, like updates can give you different answers after a time, and changes accuracy, and some kind of basic functioning of the app can in that case change. And then also if you do that, what I just said, then you rely heavily on large language models, and again something there changes or whatever, maybe your application doesn't work. And last slide. So what are the solutions to that? First is wait, because this is very new thing. Half a year is a lot. Who knows what happens in a year or two? Maybe it becomes more like stable, and there's already tools on the market that solve some things. One is version control, but again, they don't like. GPT-4 has maybe couple versions, but there's all the time changes. Like it's maybe not the best. Then adaptive design, that's kind of that you have some flexibility in the application. So they do this, I forgot what's the name, but there's somewhere where you can do multiple prompts. So you write one prompt, but then it uses actually large language model to find similar prompts to that one, and then it uses again large language model to answer those prompts, and then again uses a model that summarizes all the answers and makes you a perfect answer. So that there are ways like that. And then there's some, for this monitoring now, more and more software is coming out, and products, whatever. One is this just released, I think a week ago, this Langsmith. It's from LangChain, which has nice kind of even interface where you can monitor, and you can, for example, in case you can, let's say, write 10 questions that it needs to answer, and you record the answer of those, and you can just monitor over time. Every time something changes, you run the same questions, and then you have in that tool, like you monitor over time how was the answers and so on. So there's maybe that's one of the ways how to do that, and so on. But yeah, this is more, I don't know much more of that. I'm just going into this, so yeah, this was all from me. You have any questions? Thanks.
Yeah, thanks a lot, Davor. So please use the opportunity and now try to get your questions asked. Maybe I can ask about the large language model still. So
yeah.
This version control thing you had that. Of course, if the underlying version changes, then things are complicated.
Yeah.
But what are the difficulties if the underlying version doesn't change? If you get stuck with some model, do you then, what's the penalty that you get from there?
Yeah, but if you have made some application based on that model, then you kind of know how it should behave. So, but I mean, they maybe do some bigger changes in at least the GPT. But like if you like, we are using Azure, Microsoft Azure, and there's like OpenAI, and then if you select a model, there's only like couple versions, and that's it. But I know that there has been changes in between, but I don't have a possibility to change to that. Like that, there's no, it's not open. So, yeah.
But can you imagine cases where you would be forced to change the model? That if the underlying large language model is say 5 years old,
yeah.
is it then more or less mandatory, even if your application has?
Yeah, that's
can you imagine that you still need to change the underlying model for some safety reasons?
Yeah, I mean, you should maybe be changing them, but then maybe you should like do it in maintained way, not just during the night they have released a new version and now you're like your model doesn't work. You have like some time to maybe work on it, but yeah, the thing is that they will be changing, and that's also how to maintain then should we even use large language models for this case is a big question as well, but they are very good in many things. So I'm thinking that in many cases, they are very good to be used, but they complicate some things. And definitely they should not be used for everything. Like, let's say, you might probably know that they're very bad in simple arithmetics or something like that. And maybe, of course, they will add more parameters, more stuff, and already GPT-4 is better than 3, and 5 will be even better. Maybe they even fix that part, but why should you use that? It's kind of, I don't know, using a top-of-the-notch gaming computer for like a Lidl cashier machine. Like, it's kind of, yeah, it's not efficient. So you should maybe, but they're very good, as I said, in this understanding the context and the thing, while your basic calculator is not. So maybe you should then, when you detect that you need something to calculate, it understands maybe the context of a problem you give it, and then when it comes to the point that now you need to sum two numbers or whatever, send it to the calculator. Don't do it into the. So they're good in some things, but yeah, not to use them 100%. Yeah. Yeah.
What you use them for. So you get the predictions.
Yeah.
For say electricity consumption. Is there some like you have these obvious things like if you predict the whole day, then you heat up maybe the previous night and say the electricity cost, but you have some like non-obvious thing that you've been able to do with the predictions, or do you have some like what you have been able to optimize?
So basically, main thing here is to actually not to predict the future, but to check the history for anomalies. So main thing that they check is what already happened, and then they just want to get automatically if there is a problem in a building. So since historically this was not done, usually you had like once a month you would have your consumption value. Then maybe 10 years ago it became in EU that you should have smart meters which have every hour. I think from this or next year it's every 15 minutes you get resolution of energy consumption. But then it becomes a problem for humans, like what they have been doing up to now is manually looking into the graphs, and they every day open and they see a bunch of curves. This is how it was. And now we automate that. You don't need to, if you manage thousands of buildings, no one wants to do that. So we do here that you only look at the buildings that might have problems, and that part is automated by machine learning, and then the expert then goes to check those buildings that might have a problem. And when your question for predicting the future, as I said, that's more, for now, it's more informative. Like, nice thing to know. We can also show with the cost how much will be in euros for tomorrow. And if you are going to do something with that, it's up to you. But we don't have yet any kind of control that we will like change automatically something in a building, depending on that. But that might be a use case at some point. I don't know, is it our job or someone else's, but yeah. Yeah.
Maybe you have explained, and I didn't get it, but in this DDM,
Yeah.
Let's say we have a data of 1,000 acres, and it calculates standard deviation of 2 and 3 and all those. So for example, a change is happening in the data at index 870, so maybe it will give a warning at 850 index, because by then it has calculated
Yeah.
2, and maybe the change will not happen. It's a possibility. I'm just talking about warning, and then it calculates, and then it says 3 standard deviation, and it gives error.
Yeah.
But when you mentioned that you have your own custom this
Yeah.
checking thing, so because this thing is part of the data, but you said something about feedback. So is there like some metadata thing which is helping the original data, or how are your feedback kind of integrated in the data that it measures the change in the data?
So it's not integrated. In the feedback is not yet. That's a plan to do, but also the question is how, more than, and not in a technical way, but more in the, how to say, human-computer interaction way, how to, and the process, company process way as well, how to do that. So, as said, nowadays, I mean, the whole process of checking for anomalies is very manual. So they maybe get it by feedback from someone or something, that there might be something wrong, and then they either log in remotely to the building management system, check the things, go to the building, or call the facility manager of the building, go and check some devices there, and if there's a problem, and then they write in some of the notes, we have this kind of maintenance notes and stuff like that, they might write there like there's some problem or not, or maybe they don't write there because that's a different system. Maybe they are like we have a software for facility management, but also others have, and we might be kind of consulting on one building, but that building might have software from someone else or something else. So it's the process is not so clear. So that's biggest thing. How do we do that then? But I think first is to release this and make people use this, and then we will get over time, because we are not yet sure, are we detecting right anomalies? These are what I have knowledge, as that's also my field, and what we have got from some feedback, that these are the potential problems, but we are not yet 100% sure, and we need to kind of make people to use this, and then first manually collect feedback, but over time maybe a more automatic way how to do that. Yeah, but this method is purely just automatic, and as said, uses standard deviation and so on. But again, even if you use that, you should still do something when there's a drift. And said, let's say if the drift reason, the reason behind the drift is a problem that happened in a building, which you then after a while fixed, then you should not use that information that was during the drift, the data, you shouldn't use it anymore in training. So that's again manual process. Even if you have all these advanced methods, you still need to manually then, okay, this data is crap, remove it from the data set. Yeah.
I remember we once talked about new buildings.
Yeah.
You deal with them, but you don't have the history.
Yeah, that's a good question. If you have a new building or even an old building that has been completely refurbished, the thing is that's why you probably it will be crap at the beginning, first day, second day. But since our model is constantly training, after a while it will become better and better and better. So in case of electrical consumption, especially if it doesn't have heating, if we go to here, this is electrical consumption. It is I think office building. It's very predictable when it behaves normally. So if there's no, and it's not heating, so it's not so much seasonal. It's more or less the same, whatever is the time of the year. If it doesn't have cooling and electrical heating, then I think after a week or two you will have enough. Of course, it will still not be good, but our short model of 30 days is pretty good in this. 30 days enough. So I would say even less than that. But of course, depends on a building. Heating is a more problem because you need the whole season, the whole year, and so on. Like that's why also heating actually, when you combine long and short model, long model in heating learns relatively quickly compared to the electricity model because let's say it more depends on a temperature, and in 1 year you have maybe X amount of days that have temperature of X, let's say -15. There's couple of days, let's say. While this doesn't that much, if it doesn't have heating or cooling, electrical, it doesn't that much depend on temperature. So it doesn't care that much, is -15, -5, -10, plus. Then there's more points of the same in the training data set, and one small change will be like a small drop in the whole training data set, while in the heating, where you have only couple and then new change happens when it was -15, you had only maybe one day last year like that, it very quickly learns that. So that's one thing that I noticed.
Okay,
There
we are
yeah.
done. Thanks a lot.
Yeah, thank you.
And okay, any questions regarding the course? Everything running smoothly still, I hope. And then we continue again next Monday, and I guess next week's theme is more of the deployment of the models. So see you then. Bye. Good. Very good.
So I managed to use.
Yeah. That was.
After a few.